Welcome back to the deep dive. Today, we're sort of shifting gears. We're moving past the big philosophical why of infrastructure as code. I think we all get the benefits. And we're getting right into the operational how. We're going deep on the core muscle of Terraform, the providers.
That's a great way to put it. Think of the main Terraform engine as a central brain. It reads your code, it understands what you want to do.
Your intent.
Your intent, exactly. But that brain on its own can't talk to AWS. It can't talk to Azure or Cloudflare or, even Domino's Pizza for that matter.
Right.
Providers are those interpreters. They're specialized plugins that translate your high-level HCL code into the very specific API calls that system needs to actually create or change a resource.
They're the essential interface. So our mission in this deep dive is really to unpack the role these providers play in, a real multi-cloud world. And maybe more importantly, to look at this hidden safety net that Terraform uses.
The lock file.
The dependency lock file. It's what ensures everyone on your team and your automation is using the exact same logic. By the end of this, you should have a really solid integrated view of how Terraform handles all this.
Yeah.
So let's start with maybe the most common question you hear. If you're an engineer and you live and breathe, say, AWS, CloudFormation inside and out,
right?
Why should you even bother bringing Terraform into the mix? Why not just stick with the native tool?
And that is the fundamental question. Why add another layer? It really boils down to two things: scope and workflow.
Okay.
CloudFormation is fantastic for AWS. It's hyper-optimized for it. But that's also its biggest limitation. It only speaks AWS. And let's be honest, modern companies just don't live in one single clean box anymore.
And it's not even just about the big cloud platforms, is it? We're talking about more than just AWS versus Google Cloud now.
Oh, absolutely. Think about a real production app today. You might have your servers, your compute running in Google Cloud. Okay, fine. But your DNS, your domain name records, that's probably managed over in Cloudflare.
And you're monitoring.
You're monitoring your metrics, your logs. That's all getting piped into a SaaS platform like Datadog. So right there, if you use native tools, you're already juggling 3 different config languages, 3 different APIs, 3 different ways of doing things.
So instead of that fragmentation, that chaos, Terraform gives you one language, HCL, to manage your Cloudflare DNS, your Datadog monitors, and your Google Compute, all in the same place at the same time.
That's it. It's one tool to rule them all. That's the singular control plane you're looking for, and it makes the workflow so much simpler. And there's another piece to this, which is the transparent state management.
State management. Okay, so that's this idea that Terraform has a record of what it thinks the infrastructure looks like.
Right. The state file is like the brain of your infrastructure. It keeps track of the real-world IDs of every single resource it manages. Now, if you've ever tried to debug a problem across multiple separate native tools,
it's a nightmare.
It's a total nightmare. You're trying to figure out which component depends on which, why something didn't update, because Terraform has this one central record of all those relationships, even across different providers. Debugging is just, it's worlds easier.
That clarity alone has to save hours of just painful detective work. Okay, so let's shift from the why to the how. If Terraform has, hundreds or thousands of these providers.
It does.
For everything from Azure to Spotify,
Yeah.
How does it know which translation manual, so to speak, to download for my project? It can't possibly ship with all of them backed in.
No, it absolutely can't. And that's a core design principle. It's modular. If it bundled every plugin, the download would be huge. And worse, 99% of them would be out of date for you.
Yeah.
So you have to tell it what you need. And you do that inside your main configuration in a block called required providers, which is nested inside the Terraform block.
Okay.
And for every provider you use, you have to specify 2 really critical things: the source, which is usually the Terraform registry, and the version.
And this brings us to what I think is maybe the single most dangerous temptation in any system: versioning. My gut, and I think a lot of developers feel this, is to just say latest. Give me the newest features, the latest bug fixes.
Mm-hmm.
Why is that a potential catastrophe in an IAC world? This feels like where the real stability conversation starts.
It is absolutely the moment of truth. Let's say you define a production database using, version 5.0 of the AWS provider.
Okay.
If you leave that version wide open and an automation pipeline just grabs the latest, which is now version 6.0, you are actively inviting disaster.
Why? What's the big deal between 5.0 and 6.0? What changes?
So major version changes that
Yeah.
jump from a 5 to a 6 almost always signals what we call breaking changes. And in a Terraform provider, a breaking change could be something that sounds really simple, like renaming a resource.
Uh,
The developer might decide that Oz instance isn't a good name anymore, and in version 6.0, they change it to Odds database.
okay, I can see where this is going.
Right. The next time you run Terraform plan, Terraform reads your code, which still says the old name, but the new provider binary, 6.0, doesn't know that name. So Terraform looks at your code, looks at the state file, and it concludes, oh, this Oz instance isn't in the code anymore. I must need to destroy it.
And it proposes to destroy your production database.
It proposes to destroy your database. That's an immediate, self-inflicted, catastrophic outage. So stability has to come first, way before shiny new features.
So how do we balance that? How do we get the important security patches or minor bug fixes without opening ourselves up to that kind of destruction?
That is the whole point of version constraints. And the most important symbol you need to know here is the tilde, followed by a greater than sign. It's called the pessimistic constraint.
Pessimistic. What's it pessimistic about?
It's pessimistic about the stability of future major versions. So if you set your version constraint to, say, 5.1, you're basically telling Terraform, look, I trust any patch release in the 5.1 series, like a 5.1 or 5.1.2.
Okay, bug fixes.
Right. And I even trust minor new features in the 5.x family, like a 5.2 or a 5.9, because they shouldn't break anything. But, and this is the key, it strictly forbids jumping to 6.0. It keeps that major version number from changing.
So that's the guardrail. It lets you get updates, but prevents the really dangerous jumps. That's a great middle ground.
Yeah.
But that only solves the problem for one person, right? It doesn't guarantee consistency across a whole team.
Exactly. You've hit on the next critical piece of the puzzle. Imagine you have 5 engineers. You've all agreed on the constraint, 5.0.
Right.
Engineer A runs Terraform init today, and the latest version is 5.2. So that's what they get. Tomorrow, the provider vendor pushes a small bug fix, version 5.3. Now, engineer B clones the repo, runs Terraform init on their machine, and since 5.3 still fits the 5.0 constraint, they get version 5.3.
And now you have a problem. Same code, but 2 different provider binaries running on 2 different machines. That's the classic "it works on my machine" scenario starting to unfold.
It is the absolute definition of that problem. Your infrastructure code is identical, but the interpreter, the provider itself, is different. This is where that silent hero comes in, the dependency lock file.
Okay, so I've set my constraint, 5.0. I run Terraform in it. What actually happens under the hood that locks this down for the whole team?
So Terraform init does 2 main jobs. First, like we said, it downloads the right provider. Let's say it's version 5.2 into a local hidden directory. But the second thing it does is create or update a file named .terraform.lock.hco.
And that file gets checked into version control.
It must be checked into version control, and if you open that file, you see a bunch of information and then these long, random-looking strings of characters. Those are the checksums or cryptographic hashes.
Okay, this is a key detail. Why is it storing a hash of the file instead of just writing down the version number, 5.2?
Because the version number alone isn't a strong enough guarantee. Imagine the vendor releases 5.2, but an hour later they find a tiny mistake in how it was compiled. They might quickly fix it and re-upload the file, but still call it 5.2. Ah, I see.
So a developer downloading the new 5.2 would have a physically different file, even with the same version label. The lock file doesn't trust the label. It fingerprints the binary file itself. It guarantees that every single person and every automation job is using the exact same byte-for-byte copy of that provider.
Wow, so just to make sure I'm following this, we're not just checking the version number, we're checking the file's DNA to make sure it's the identical piece of software for everyone.
That is a perfect analogy. It's the DNA. If engineer A gets a binary with hash X, the lock file records hash X. When engineer B runs a neat, Terraform sees that hash in the lock file, downloads the binary, and then checks its hash.
Yeah.
If they don't match, Terraform stops. It fails the initialization.
That's incredibly powerful. So let's connect this back to the constraints, because this is where the workflow really comes together. If my constraint is broad, like 5.0, and the first person gets version 5.2, does that lock file then pin everyone to 5.2, even if 5.3 is released later? That is exactly what it does. The moment that lock file is written, it takes precedence. It effectively pins that broad constraint to the specific version that was first initialized. It removes all ambiguity for the rest of the team.
So if we actually want to get the new features in 5.3, we have to do something intentional. We can't just run a normal Terraform in it.
Correct. You have to take a deliberate, conscious action. You run Terraform init upgrade. That upgrade flag is you telling Terraform, hey, I know the log file says 5.2. I want you to ignore that for a moment, find the newest version that still fits my constraint, download it, and then update the log file with the new hash.
It forces you to make an explicit choice.
It forces intent. And that protects you from accidental drift, which is fundamental for any serious system.
This has been a fantastic deep dive. We've really gotten into the weeds of what can feel like a background process.
We have. We've really unpacked the muscle and the safety net of Terraform. If you walk away from this with just 3 things, it should be these. First, providers are plugins. They're the interface between Terraform and, well, everything else.
Second, and this is the stability piece.
Configuration is specific. You absolutely have to use that required providers block, and always, always use the pessimistic constraint, to stop those breaking changes from hitting production.
And finally, the thing that makes teamwork possible.
The lock file is law. That .terraform.lock.hcl file uses hashes, those checksums, to guarantee that every single person is on the exact same page. It's what makes collaborative infrastructure as code actually work.
So thinking about the bigger picture here, if this lock file is quietly ensuring that your whole team, no matter where they are, is using this identical verified logic, what does that unlock? What new possibilities for scaling your infrastructure or creating standardized templates open up when you completely eliminate that variable of, well, it's different on my machine? That's something to think about as you move forward.